good afternoon, good morning, wherever you're watching this. This is a question on shear force diagrams. So it's shear force, so it's determining the shear force on a beam. We'll call it a beam. It could be an axle, it could be just a bit of metal supported, but we'll name it a beam. Simply supported beam, it's simply supported here, look. It's got 2-point loads. So the 4 and the 3 are point loads. No UGL at the moment. There's no uniformly distributed loads. Beam is 10 meters long. It's 2 meters to the 4 kilonewtons, and then another 4 meters to the 3, and then 4 to the end. Total length is 10. So we've got a draw or sketch. There is a difference between drawing and sketching. Draw the shear force diagram for the beam. Actually, I'm sketching it, so draw means use a bit of graph paper perhaps. So in theory, I'm just sketching it. Still use a ruler and measurements though, but I am sketching. So first of all, we've got to work out these two reactions, reaction A and reaction B. So that's the first thing we've got to do. So hopefully remember how to do that. That's why calculating reactions is very important, because if we can't do this, everything else will be incorrect. So the first of all, we'll work out RA and RB, and then we can do the shear force diagram. So like we normally do with reactions, assume this. Sum of the forces equals 0, which means that we've got 4 and 3 coming down. So 4, 5, 6, 7. 7 kilonewtons coming down, which means we've got to have 7 coming up. So RA plus RB has got to equal 7. Because we've got 7 coming down, which means we've got 7 coming up. Otherwise, the beam will go down, crash through these supports. So sum of the forces have got to equal 0. The sum of the moments have got to equal 0. It's not a seesaw. We don't want this beam to be bending and tipping, so we assume it's going to be in balance. So there's going to be no clockwise moments on it, or anti-clockwise moments. So it's not going to be spinning or stuff like that. Sum of the forces equals 0, sum of the moments equals 0. Clockwise is positive, anti-clockwise negative, just like we've always done. The beam is in balance, or the beam is in equilibrium, and moment is force times distance. So that's standard stuff. Again, you can call clockwise negative if you want to, it's up to you. So first of all, we'll do RA and RB. So calculate RB by taking moments about point A. So calculating RB first, this will be my pivot point. That's going to be my pivot point. So it's fixed at point A, and then these forces are going to spin it, or try to. So if I'm fixed at that point, that 4 kilonewtons is going to try and make this go anti-clockwise. No, it's not. It's going to go clockwise because it's going to go that way. The 3 kilonewtons is also going to make this beam try and spin that way because it's fixed about that point, so it's trying to go that way. The 4 is trying to go that way. The 3 is trying to go that way, so they're all clockwise. They're going to be positive. And then this force here, which we're trying to work out, this RB, is trying to push it that way, spin it that way about this point. So that's going to go in an anti-clockwise direction. So that moment there is going to be anti-clockwise, so we'll call it negative. Don't forget, moment is force times distance. So there's my forces, there's my forces, there's my forces, and my distances are here and here. So the 4 kilonewtons is 2 meters away from this. The 3 kilonewtons is 4, 5, 6 meters away from that point. And then this reaction B, that force B is 10, 8, 9, 10 meters away. So here's my first moment. It's going to be the 4, it's 4,000 really, so you can't just put the 4 in as long as you remember it's K. So 4,000, because that's my force, times by 2, because it's 2 meters away from this point. For some distance, 4,000 times by 2. It's going clockwise, so we'll leave it as a positive here. Like, there's no negative number, that's just positive. Sum of the moments have got to equal to 0, so we've got to add them all up. So add is my 3,000, it's 3 kilonewtons. You can put 3 if you want to, just don't forget to put the K in at the end. I've got 3,000, and how far away is this 3,000 to there? 4 and 6, 4 and 2 is 6. So it's 6, so it's 3,000 times by 6, force times distance. There's my force, here's my distance, 4 and 2. It's going clockwise, so it's going to be plus. Again, that's 1 and 2. We've also got a reaction here. The reaction is trying to push up and try and go anti-clockwise, so it's going to be negative. Here's my force. We don't know what it is. We're trying to work it out, so I'm just going to put it in, RB. Distance is going to be, how far is this force here from my pivot point? 8, 9, 10 meters. So it's force times distance. It's going anti-clockwise, so you can put a negative there, or if you want to, you could put a plus there, and as long as you put a negative in front of the RB, it works out, because we are adding up the moments. So some of the moments, so we're adding these up, have got to equal 0, because the beam is in equilibrium, so make sure you put 0 there. So now just work these out. So we'll do it like this. You could do it in your head if you want to, but so 4,000 times by 2, there's that one, plus 3,000 times by 6, 3,000 times by 6. We can't do much with this because we don't know what that number there is, so we'll press equals 26,000. So 26,000 really minus RB times by 10 is 0. This is a negative term, so I'll bring it across to there to make it positive. I'm going to add RB times 10 to both sides, which means it gets rid of it there. So we get rid of it there and it comes over here. So 26,000, because that plus that is 26,000, equals RB times by 10. Therefore, them 3 dots means therefore, I'm going to bring the 10 down to here and leave the RB by there. So 26,000 divided by 10, get rid of that, get rid of that. So 2,600. If you don't believe me, 26,000 divided by 10, you should need a calculator for that. So reaction B is 2,600 or 2,600 newtons, or 2.6 times 10 to the 3, or 2.6 kilonewtons. So thank you very much. We put that in, so make a bit more space by here. So if we can do it with a pen, so we've got 2.6, don't forget the K, coming up. So we've got 2.6 coming up. Now we need to work out RA. What you could do is you could, if you're confident that that 2.6 is correct, which you may not be confident, and you shouldn't be unless you've checked, we could say that we've got 7 coming down, which means we've got 7 coming up. So RA plus RB has got to equal 7. So we're expecting, so there's 11 coming down. We know that RB is 2.6. So if I take away that, can you see the green? 11 take away 2.6. 11 take away 2.6. That's going to give me RA. RA 8.4. Which we could do it that way, but this, if 2.6 is incorrect, then that 8.4 is incorrect. So what we've got to do now is take moments about this point. So we'll do the same thing, take moments about point B to find RA. We're hoping it's going to be 8.4. Just to make sure, because we've sort of checked, we've worked out that 11 take away 2.6 is 8.4. If that 2.6 is correct, when we work out this reaction here, if it comes to 8.4, we know we're 99% correct. So it's going to be force times distance again. Here's my 3 times 4, because we're going to go about this point now. Point A, point B is going to be the pivot. So 3 times 4 is going to be going that way. So it's going to be anti-clockwise, negative. That 4 is also going anti-clockwise, negative. And RA is going to try and spin it clockwise. So that's going to be positive. There's 3,000 times by 4 and 4,000 times by 8. And this will be RA times by 10. So the same process really. There's something wrong up there. Let's have a look. 4, 5, 6, 7. There we are. I can't count. Always check, look. I don't know why I've done that for. Can't count, can't add up. So 4, 5, 6, 7. We've got 7 coming down. So 7 coming down. So 7 take away 2.6. So always check, always check. 4.4. So I'm hoping we're going to get 4.4 for RA. I don't know why I put 7 in there for. I mean 11. So we've got 7 coming down. So RA plus RB has got to equal 7. I know this is 2.6. At the moment I know it's 2.6. Could be wrong. And I'm hoping that RA is going to be 4.4, which will make my answer correct. So, so here we go. RB is 2.6, 4.4. So it works out, looks. Hindsight. So calculate RA by taking moments about point B. So 3,000 times by 4. There's my 3,000 times by 4. It's going anti-clockwise. That's why I got a negative number there. The next one, plus, is going to be 4 times by 8. So 4 is the force, 4 killer, 8 is the distance, 4 times by 8. Don't forget, we're adding up the moment, so plus, this is going to go anti-clockwise, that's why I put a negative number there. So it's going anti-clockwise, anti-clockwise, and then the last one is RA. RA is going to go clockwise, and it's 10 meters away. So it's 10 meters away. So it's going to be RA times by 10. It's going clockwise, so it's positive. So we'll all add that up, make sure it's equal to 0. The sum, we're going to add all these up, equal to 0. If you add these up properly, so if we do it one quick one, two, we'll do minus 3,000 times by 4 plus minus 4,000 times by 8 close the bracket, minus 44, so thank you very much, minus 44 plus RA times by 10 equals 0. This is a negative term, so we'll bring it across. We'll add 44,000 to both sides. So now we get RA times by 10 equals 44,000. We want to find what RA is, so divide both sides by 10. So we get rid of that and we leave the divide by 10 over here. So the reaction at point A is going to be 44,000 divided by 10. So get rid of that one, get rid of that one. 44, 44. Obviously the minus just means direction, so 44 divided by 10, you should need the calculator for this. 44, or you could press that, ENG, 4.4 times 10 to the 3 newtons, which is kilonewtons, which 7 take away 2.6 is 4.4, so I'm quite happy that we're sort of correct. So we've got 4.4 coming up there. 4.4 coming up, killer. So just to check that, because it's always good to check, we know that the sum of the forces have got to equal 0, so whatever's coming down has got to be going up. So we know that RA plus RB has got to equal 4 plus 3. So RA, here look, plus RB has got to equal 4 plus 3. So there's 7 coming down, which means there's 7 coming up. So it's looking good because 4.4 plus 2.6 gives me 7. So RA plus RB has got to be 4 plus 3 because 4 plus 3 is coming down and these are coming up. So you could say these are negative numbers coming down and these are positive coming up. So 4.4 plus 2.6, 4.4, 2.6 equals 4 plus 3, which does. So that plus that gives you 7. So 4 plus 3 is 7. So I'm quite happy that my reactions are correct. So RA and RB we now know, so we can use them now to plot our shear force diagram. You need to make sure that you're confident that your reactions are correct before you start moving on to the shear force, because if they're incorrect, your shear force diagram is going to be incorrect and you won't really know until your diagram is wrong and then it'll start again. So you need to make sure, do it 3 or 4 times just to make sure that your reactions are correct. Because God forbid you started drawing the diagram and had to do it all over again. What would the world come to? So, shear force diagrams, don't forget, we start from the left of the beam. So all we're doing is looking at the shear force. We'll start from the left. I'm going to leave them on there. I leave the 4.4 on there. All right. So I'll get a bit of space here. Get rid of all that. I can get a bigger one though. So what we'll do is, like we've done before, like we've done in class, 4.4, 4.4. We'll start off here. So we'll start off at x equals 0. The left of the beam is here, so x equals 0, and then we'll go up. So we're going to go up in, we'll go up in 2s, 2, 4, 6, 8, 10. Nice easy numbers. You can go, it's up to you, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You could even go 0.5, 1, 1.5, you know, go up in millimeters, you know, it'll be loads of a graph if you go millimeters. You need to go up in, you know, 2 meters, 1 meters, depending on the graph, depending on the beam. I always make sure you go where there's a force or where there's the center of the bending or something like that. So in this case, I'm going to go x equals 0, x equals 2, x equals 4, because x equals 6, because we've got 4 at 6, x equals 8. So 2, 4, 6, 8. Who do you appreciate? 2, 4, 6, 8, 10. We'll start off at x equals 0, and what we do is we look at what we can see at that point. So at x equals 0, the shear force, all I can see is this 4.4 coming up. That's all I can see. See if I can put a shape on here. So I put a blackout shape. No, I can't. What is that then? Oh, I think that's just that, isn't it? Oh, hang on. Just to do this. So if I put a shape like that now, let's see if it works. I don't know what I'm doing. Does it turn it into a square? That's what it does, is it? Do you go into a square? Yes. Can I move it then? No. So we get rid of that. So we'll start off at x equals 0. What can I see at x equals 0? Well, all I can see at x equals 0 is this force coming up. That's all I can see at x equals 0. I can't see anything else because you can't see it. At x equals 0, all I can see is 4.4. So x equals 0, the shear force is 4.4 kilonewtons. That's the point we're going to put on our graph. X equals 2, I'll go to x equals 2. So I'm here now. So at x equals 2, right, all I can see, forget all of this, you don't need, right? So all I can see at x equals 2 meters, all I can see really is this 4.4 coming up and then this 4 coming down. That's all I can see. Because all I'm looking at is what I can see at x equals 2. I can see that force coming up, 4.4, and I can see this 4 coming down. So we're going to get 2 points. We're going to get 4.4, and then we're going to get 4.4 take away 4. So I can see 4.4 coming up and the minus 4 coming down. So 4.4 take away 4 is going to give me 0.4. Now on the graph there's going to be 2 points. There'll be the 4.4 and then there'll be another point of 0.4, which you'll see on the graph in a bit, right? So there's 2 points. When you've got a point low, there's 2 points. So that's good. So at x equals 4, what can I see at x equals 4? Now don't forget, all I'm doing now is looking at what I can see at x equals 4. And x equals 4 is here somewhere. 2, 4. So it's there. So what can I see? I can see the 4.4 coming up and I can see the 4 coming down. That's all I can see. So nothing's changed really, because we've got no weight of the beam, we just got point loads. If there was a weight to this beam or a UDL, we haven't got one, but if there was, it'd be a different story. So we've got 4.4 coming up and 4 coming down. So at x equals 4, we've got 4.4 minus 4 is 0.4 still. Because there's nothing else. There's only 2 forces, one coming up, one coming up, and one coming down. Different story now when we get to x equals x. So at x equals x, x equals x. I'm just looking now what I can see at x equals x. X equals x, x equals 6. So 2, 4, 6 is here. So what can I see? Well, I can see this 4.4 coming up. I can see the 4.4 coming down. So I'll have a point for that. And I'll also see as well this 3 coming down, because I can just see that 3 coming down. So I'll have 2 points. I'll have 4.4 take away 4. That'll be 1 point on my graph. And then I'll have 4.4 take away 4, take away 3. So I'm going to have 2 points now. So that's my that's my reaction. 4.4 take away 4. It'll give me 0.4. And then as well, you can include on another line, I've got 0.4 take away 3, because there's the 3 coming down here. That gives me minus 2.6. So I'm going to get 2 points. I'm going to get 0.4 and I'm going to get minus 2.6. Just check that. Always check things as you're going along. No, we're doing minus 3. 2.6. So I'm going to get 2 points. Whenever you've got a point low, there are going to be 2 points, which you'll see on the graph in a bit. X equals 8. Well, there's nothing much happening at x equals 8 because there's no force there really. No new forces anyway. So at x equals 8, which is going to be here. 2, 4, 5, 6, 8. It's going to be there somewhere. So all I can see is the 4.4 coming up still, the 4 coming down, and the 3 coming down. There's nothing else. There's no UDL, remember? In a video coming up soon, we'll have a weight to this beam, so that changes a few things. But all we've got now is 4.4 coming up, and we've got 4 coming down and 3 coming down. At x equals 8. 4, 5, 6, so there's going to be about 2 in there somewhere, roughly. X equals 8. 4.4 minus 4 minus 3 is no different to that because there's nothing else happening. So that's good. Minus 2.6 kilonewtons. Don't forget units. X equals 10. We've got a few things happening at x equals 10. So at x equals 10, which is going to be there. So it's the entire length of the thing now. So at x equals 10, we can see all of this. We can see 4.4 coming up. We can see that 4 coming down, that 3 coming down. That's going to give us 2.6 minus 2.6. And we're also going to get another force because there's a force here, look. 2.6 coming up. So we'll have another point. Now, this beam is in balance, so hopefully our numbers come back to 0. So whatever number you get here, it should be a minus number, and it should be equal to this force here, which we know is correct because we've got minus 2.6. 4.4 take away 4 take away 3 gives me 2.6 minus 2.6. That'll be a point on our graph, and then this force kicks in coming up. So minus 2.6 plus 2.6 should give us 0. So on a shear force diagram, it should really start off at 0 and end in 0. Obviously, if you've got 0.1 or 0.05, it's just your roundings may be slightly out. So it's looking good for our graph. Now, if your reactions were incorrect, you would see that mistake there. That's why you need to make sure your reactions are correct at the start. So at x equals 10, I've got 4.4 minus 4 minus 3, which gives me minus 2.6. So that's 1 point on my graph. So we've got 2 points. Syntax error, that's the answer. Overdone. Minus 4 minus 4 minus 3 minus 2.6. So we're going to get minus 2.6. And then we're going to get this, minus 2.6. And then we've got this force here kicking in, which is this reaction here coming up, which is 2.6 plus 2.6, which will give me 0. So we know we're correct. So when you're doing this, if you get to the end of the beam and it's a minus 2.6 here, whatever the number you get here, hopefully it's a minus equivalent to the reaction coming up. So that's a way of making sure that you're correct. For a simply supported beam, obviously we'll have overhangs soon, so that might change a few things, but as far as for now, just as a way of checking. So now I'm going to plot these numbers. So I'm going to go on my I'm going to draw a graph like this, easier on graph paper, but times are hard. So x equals 0, I'm going to plot 4.4. Don't forget it's kilo, right? So x equals 0 in meters. X equals 2, I'm going to plot 4.4 and 4, 0.4. X equals 4, I'm going to plot that. X equals 6, I've got 0.4 and minus 2.6. X equals 8, press the pause button. I'm back on, I hope. So, and then that gives me minus 2.6. And then 10 is going to be minus 2.6 and 0. So on my graph, here's my graph. shear force coming up. So I've got to go up to about 4.4, so I'll go to 5, and I've got to come down to about minus 2.6. So I've gone up 1, 2, 3, 4, 5 kilonewtons up, and 1, 2, 3, 4, 5 down. So there's enough room there for me. 10 meters, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x meters. So my first point is going to be, there's a point there really, and then so my shear force diagram is going to look a bit like this. So 4.4 is there, x equals 0, 4.4, plot 4.4. So we'll have it coming up, starting from 0 really up to 4.4, because 4.4. Then at x equals 2, I've still got 4.4. But don't forget, I got 2 points, so now this is where my 4 kilonewtons kicks in. So I come down to 0.4, bang, down, across comes the line, and down it comes. That's the point load. So it comes up 4.4 across, and then when the 4 kicks in, it comes down. Don't go from there to there. You need to, this comes across and straight down. There's 2 points. So now x equals 2, really, we've got nothing happening now until we get to about 3 kilonewtons and 6 meters in. So at 4, we've got 0.4 still, so nothing happening, really. So there's a point there, x equals 4. So put it in if you want to. I don't know why I haven't put it in. 0.4. So there's 0.4, and then we get to x equals 6. So we'll still have this. We'll still have this 0.4 here. Still have that up, that down, that across. So 0.4 is going to be there. X equals 6. Don't forget we've got this 3 kilonewtons kicking in. So this 3 now comes down. So minus 3 gives me minus 2.6. So 0.4 down to minus 2.6. So that's my 3 and my 4 kicking in. X equals 8. There's not much happening at x equals 8 is there, because it's still 2.6 still. So that's still minus 2.6. So there's nothing happening until we get to the end really. So it's going to be steps at 2 and steps at 6. So steps at 2 and steps at 6, like step down. X equals 10. We're going to get 2 points. We're going to get minus 2.6, and then we're going to get 2.6 coming up, because we've got this force here coming up. So minus 2.6, and then we get this coming back up to 0. So there's my 0. So 2 points, minus 2.6 and 0. And that's my shear force diagram. If you notice, it comes up, the reaction of RA, it comes across, comes down, equivalent to that load of 4, comes across, nothing happening. Then the 3 kicks in, it comes down, nothing's happening, and then it kicks back up with the 2.6. No UDL. This is just point loads. It's slightly different when you've got a UDL, but for now we haven't got any. So it goes up a force, across, down a force, across, down a force, across and up. One last thing, which is very important. At this point here where it crosses at x equals 6, that is where there's no shear force. So that is where maximum bending moment would happen, because there's no shear force. So all the forces are being put into bending. So when we do bending moment diagrams, if we do this diagram, which I probably will, you will probably see that the maximum bending moment is at x equals 6. So where this shear force diagram crosses the axis, so shear force is 0, that's where the maximum bending moment would be, and that's where failure may occur due to bending. So at x equals 6 meters in from here, or 2 from there, look, shear force is 0, so that point there is the maximum bending moment or the minimum shear force. So when you're drawing shear force diagrams, make sure you label these points correctly. Make sure you put units in correctly, make sure it adds up to 0 at the end. The main point though is to make sure you get your reactions correct and your reactions correct here. Like I say, this is only a beam with 2-point loads, no UDL. Future videos will be with a UDL, so it gets a bit different then. So over and out.